Hello, today we're going to chat about solving using the quadratic formula. Now, in the past, we have done a couple different methods thus far for solving quadratics. We've talked about factoring, and we know that with factoring, this sometimes works because sometimes not everything is factorable, and we would call it prime or unfactorable. So we had to use some different alternatives. We then talked the other day about completing the square, and we can complete the square always. But as you may have found out doing your lesson work, that sometimes completing the square can create some pretty ugly fractions. And not only that, but there's a lot of room for error. So using completing the square can be useful when we have equations where there is nothing in front of x squared, and when we have the middle number b is an even number, so it's evenly divisible by 2 when we're completing the square. Another good method that we're going to talk about today is the quadratic formula. And the quadratic formula always works. It's a little bit time consuming, but it works every single time, and it gives us the most accurate of solutions and a lot less room for error. So here's the quadratic formula. You may have seen this before, but it is x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. And we have to make sure that our quadratic equation is set equal to 0. And ideally, I'm just pulling the coefficients in front of x squared in front of x and the number by itself. And you can see that they're placed strategically within the formula. So let's start off with x squared minus 5x minus 2 equal to 0. So I see that it's already set equal to 0, and now I'm going to pull the coefficients out. So the coefficient in front of x squared, even though I don't see it, is 1. The coefficient in front of x is negative 5, and c, the constant by itself, is negative 2. So a is 1, b is negative 5, and c is negative 2. And I'm going to start inserting them into the equation here so that we can simplify. So x equals opposite of b. So the opposite of negative 5 would be positive 5. So x equals opposite of negative 5. So x equals 5 plus or minus the square root of b squared, so negative 5 squared, minus 4. 4 is just a number that's listed there. Just use it as part of the formula, times a, which is 1, times c, which is negative 2, all over 2 times our a value, so 2 times 1. At this point, it's just a matter of using the order of operations to simplify. So we're going to start inside the radical there to start simplifying. So I left everything the same. I'm going to start with the exponent. So negative 5 is squared is 25 here. Then we'll move to the multiplication. I also took 2 times 1 and got 2 in the denominator. Then I will take negative 4 times 1 times negative 2, which turns into positive 8. Then we'll add inside the radical, so 25 plus 8 gives me 33. I see at this point I cannot reduce my radical. I don't have common numbers to simplify the fractional parts, but I know that I do have 2 answers here. I have one answer where we have 5 plus the square root of 33 over 2, and where x is equal to 5 minus the square root of 33 over 2. Let's try negative 5u squared minus 15u equal to negative 10. This is not set equal to 0, so to do that I will add 10 to both sides, giving me negative 5u squared minus 15u plus 10 equal to 0. Now we can pull the coefficients. So a is equal to negative 5, b is equal to negative 15, and c is equal to 10. We can now place them into the formula. So x equals, or it should be u equals, opposite of b, so the opposite of negative 15 is positive 15, plus or minus the square root of b squared, so negative 15 squared, minus 4 times a, which is negative 5, times c, which is 10, all over 2 times a, which is negative 5. Again, now we'll start on the inside of our radical with the square. So negative 15 squared gives us positive 225. Then we can multiply negative 4 times negative 5 times 10, giving us a positive 200. Notice I also took 2 times negative 5 to get negative 10 for the denominator. I can now add inside my radical, so 225 plus 200 is 425. I know that 425, we need to simplify somehow. So the largest perfect square number that divides into 425 is 25 times 17. I can take the square root of 25, which we know is 5, giving me 15 plus or minus 5 square roots of 17 over negative 10. I now look at the outside numbers here. Each one of these are divisible by 5. So I'm going to clean this up a little bit. I'm also going to move that negative out in front of my answer so that it's not kind of in the way in the bottom. So I moved my negative to in front of the radical, or in front of our fraction, and then I divided each one by 5. So 15 divided by 5 is 3. 5 divided by 5 is 1. We don't necessarily need to put that 1 in front. And 10 divided by 5 is 2. Let's try 2x squared minus x plus 1 equal to 0. So I see this one is already set equal to 0. So I can grab the coefficients. A equals 2. B is negative 1, even though I don't see the 1 there, we know it exists, and C equals 1. Now we'll start placing this into the quadratic formula. So x equals opposite b, opposite of negative 1 is positive 1, plus or minus the square root of b squared, so negative 1 squared, minus 4 times our a value of 2 times our c value of 1, all over 2 times a, which is 2. So I'm going to multiply this 2 and the 2 together, and I'm going to take this square, so I'm going to kind of simplify a little bit. So 1 plus or minus negative 1 squared is 1, and then down here 2 times 2 is 4. Then I will multiply inside my radical, giving me negative 4 times 2 times 1 is negative 8. Subtracting inside my radical, 1 minus 8 is negative 7. We can simplify this. Recall that negative 7 is the same as negative 1 times 7, and we replace the square root of negative 1 with I. So the square root of negative 1 becomes I square root 7. And I have 1 plus or minus I square root 7 over 4. Notice that all of these are not divisible by the same numbers, so at this point we're done, knowing that we do have two solutions here. 1 plus I square root 7 over 4 and 1 minus I square root 7 over 4. Sometimes our functions or our quadratics aren't in the form, so we have to manipulate them, perhaps multiply, distribute, get rid of parentheses, combine like terms. So I'm going to start with distributing my y here to get rid of those parentheses, giving me y minus y squared equals 1 minus 6y squared. Now I'm going to subtract the 1 and add the 6y squared and bring them to the left-hand side so that this is equal to 0. At the same time, I'm going to combine like terms. So if I have negative y squared and I add 6y squared, I now have 5y squared. I can bring down the y, the positive y, and I don't have anything to subtract 1 from, so it's just going to go to the end. And now we're set equal to 0, so we can grab the coefficients. So a is 5, b is 1, and c is negative 1. And now we can put them into the formula. So y equals opposite of b, so the opposite of b is negative 1, plus or minus the square root of b squared, so 1 squared, minus 4 times our a value of 5 times our c value of negative 1, all over 2 times a, which is 5. So I'm going to multiply in the denominator, and I'm going to square on the inside to start simplifying. This gives me y is equal to negative 1 plus or minus the square root of 1 minus 4 times 5 times negative 1 over 10, since 2 times 5 is 10, I'll multiply inside the radical. I'll take -4 times 5, which we know is -20, times 1 is -1 is +20. So on the inside now I have 1 plus 20. I can go ahead and add inside my radical. So 1 plus 20 gives me 21. I cannot reduce the square root of 21. So at that point, I see that we can't simplify any part of our fraction. So we're done with our two answers here, -1 plus the square root of 21 over 10 and -1 minus the square root of 21 over 10. You probably noticed something unique inside the radical. So inside here will tell us if we're going to have real numbers or maybe perhaps complex answers. So there's a special thing underneath the radical, this b squared minus 4ac. This part is unique because it's called the discriminant. The discriminant can tell us a few things. It can tell us, for example, what type of solution we will end up with. So if we have b squared minus 4ac, and the number is greater than 0, so we have a positive number underneath the radical, we'll end up with two real number solutions. If we have a negative underneath the radical, so our number is less than 0, we will have two complex solutions or imaginary solutions. So we would expect to see the letter I. If it is set equal to 0, so if we multiply and we square underneath there and we get the answer of 0, we'll have one real solution. So keep this table handy with you. Let's determine the type of solutions the equation will have. So I have x squared plus x plus 2 is equal to 0. So it's set equal to 0. I still need to know what a, b, and c are, so I can plug them into the discriminant. So my a value is 1, my b value is 1, and my c value is 2. So I'll plug them into the discriminant, giving me b squared, 1 squared, minus 4 times a, which is 1, times 2, which is our c value. And then it's just a matter of using the order of operations. So squaring first, 1 squared is 1. Then we can multiply. -4 times 1 times 2 is -8. 1 minus 8 is -7. So here I see that we ended up with a number that is less than 0. We have a negative number. This tells me that we're going to have two complex imaginary solutions. Let's try 3x squared minus 8x plus 2 equal to 0. So it's set equal to 0. We still need to find a, b, and c before we plug it in to b squared minus 4ac. Our a is 3, our b is -8, and our c value is 2. We plug them in, so b squared, so -8 squared, minus 4 times 3 times 2, which is our a and our c. Squaring first, we have 64, so -8 times -8 is 64. Minus 4 times 3 times 2. So if I take -4 times 3, we get -12, times 2 is subtract 24, and 64 minus 24 is 40. So here I ended up with a positive number, so a number that's larger than 0. This tells me that we're going to end up with two real number solutions. Now, if we may not have nice whole numbers when we take the square root, but we will have two real number solutions. And that wraps up using the quadratic formula along with the discriminant.